All right. This is going to get recorded for any of you that want to see parts of the review. I'll throw it into a YouTube video and you can have it. If you don't use it, so be it. A little bit of God's Word. Ephesians 2:10 says, we are God's workmanship created in Christ Jesus to do good works, which God has prepared in advance for us to do. Let's go a different direction than where some of you heard me talk about this today. Have you ever seen the results of your good works to this point in your life? And I would hope the answer is yes. So maybe you're a hypothetical Camp Phillip counselor and you see kids that are on fire about whatever the theme is and ultimately the Bible. You have a little experience with EFE things and you see students that teach or are understanding what you've done. You have Mother's Day coming up on Sunday, and you can think of Mother's Day in the past where you could tell your mom knows that you love her. This passage obviously can go a lot deeper if you're thinking into things like, how does that affect your ministry? Like, can you already see the kid that's going to come to you in high school that says, that was the best explanation I've ever heard. That group work was more engaging than I've ever seen. Can you already see this person is going to say, I want to be a teacher because of you? Or even deeper, you helped me through some rough times and ultimately showed me Jesus. Because good works aren't just good works, they're things that are done out of fruits of faith. And I love this passage because it forces me to think about things I haven't even pondered yet, that God already knows I'm going to do because He's prepared in advance that I'm going to do them. Cool passage. We're going to start with Matt, and you're going to lead us through, it looks like, the last portion of the capstone from 6.5, especially...
That's what you had said to focus on.
Angle transformations in 3 dimensions. Have the mic.
Okay.
Put it somewhere.
Also, we should probably talk about how what we did yesterday and what the book says is kind of opposite for some of the things. Because it might have to do with our order. Where did we put our transformation thing? Do we put it before or after?
Teach what you'd like to, and then I'll fill in the blanks.
Okay. So, here we have transformations in R3 with cosines and sines and stuff like that. So that makes us immediately think, well, we're going to be doing some sort of rotation. So, let me ask you. Maybe you peeked ahead, maybe you didn't, maybe you know, but which one of these do you think we're rotating around what? So for J, which one? Caddy? Yeah, J would be the x-axis. What about K? Somebody else, yeah. The y-axis, yeah. What about L? Hang on, there's only one left. Yeah, Carl. Yeah, the z-axis. So, I don't know, one thing that I thought was pretty cool was when I thought of doing a determinant of this, and you go, you end up crossing out your x there, and then you're left with yz as your angle things. Same thing here if you go like that. It leaves you with that. And same thing here. It's kind of cool that happens. I don't quite know how that works or plays into it. So that's pretty cool. I also multiplied it out in one of these things to just see what it looks like when you take this transformation, on x, y, z, and you end up with this cosine theta x plus sine theta y for your x component, this negative sine x plus cosine theta y for your y component, and then just plain old z. So z stays the same. And then somehow these are working together to rotate it, and I think this way it's counterclockwise, is what the book said. You're going counterclockwise by theta. I'm not sure how that addition and that subtraction ends up working out to produce that. It must have something to do with both cosine and sine being taken of both of them at the same time as you do that. as I was going through this, it was for the shears, I think, where we said it was the opposite of what the book said. But it depends on how you do your multiplication, I think. So you can define, if you're defining your multiplication as this as your transformation times your column xy, then it's one way. But if you do, and I think the thing was we were doing it kind of vectory, like an x1, x2, y1, y2, where in here they were just doing a column xy. And it might depend on whether or not we were doing column vectors or row vectors for it too. So there's a whole bunch of things, maybe our definition wasn't wrong, but it wasn't how they defined it in here.
You talked a little bit about it matters whether or not you have the matrix first multiplied times what you're looking at, or whether or not you do it second. Can you speak a little bit to basically like A through I from this problem? Is there any difference in what we talked about, or anything that came to your mind as you're going through problems at all about the rest of the story? You mentioned shears a little bit.
So for some of them, it made a difference. Some of them it didn't. I don't know, it depended on how I did my multiplication. Like, did I use an x1, x2, or a y1, y1, y2, and the orientation? I didn't go through all of the different permutations that you could have. But there were a couple of times where, oh, that isn't quite what I was expecting. That's not quite right. So then I redid it. And eventually I was able to finagle it into the way that it's supposed to be. But it makes a difference for most of them. I don't think there's anywhere it... There isn't never a way that you can... Hang on. There's always a way that you can screw it up if you do the multiplication wrong.
Any other points you want to make?
I don't know. With these rotations, I thought it was cool, how it aligned like that. Can you speak a little more to that? I didn't really find too much. No? Okay.
Sounds good.
Cool connections.
Oh, Jason.
Yes?
Why is there one or...
For here?
Yeah.
For here, here, and here? Because as you multiply it out, you still want to have that z, or your y here, or your x here. So every time that you take, when you take this multiplied by your, x, y, z, what you're going to end up with, as we do that multiplication, so that you end up with x in the part where you want it to stay the same. Because you're rotating around that x-axis, or you're rotating around that y-axis, or you're rotating around that z-axis.
I see.
Yep. So your z's need to, when you're doing this one, your z needs to stay the same.
So, yes, you need the x and y and z to stay the same. Nice job. 1, 2, 3.
Oh.
I want to get to the final review thing. I'll take your lanyard.
There you go.
So the basic ideas of what's going to happen with transformations will stay the same.
I need 4 volunteers. Lash,
already
Matt.
up.
Oh yeah,
Already
you
up.
guys.
I'm assuming that if you have your hand up and you walk to her, she wants.
I'm gonna fold this in half. Hold on. Hold on.
How you roll.
Okay, grab a corner. Make sure that everyone can see you. Grab a corner, ladies. Okay, so I wanted to talk about the transformations a little bit more. I know in class yesterday we talked about shears and I didn't really understand what was going on. Yeah, so figure out how you're going to set up the shape. Just hold it tight. I can't see. I don't know what's going on. There you go.
We should be wearing that.
Yeah.
Just put it like on.
Okay. So I wanted to talk about different transformations. So x-axis would just be moving it and then flipping it and things like that. Yep. Keep it tight. Yep. So this would be in 3D. Let's say that this is vertical. Put it up and down. Okay, so if we were rotating around in 3D, we can rotate like this. Rotate like 45 degrees. Or that. Don't turn. Just turn for me. There we go. So that'd be a rotation. And if you wanted an expansion, pull it down. Expansion. Here, Lash, you can hold it. I'm sorry. Pull it nice and tight. That'd be an expansion to expand it out. And then would be, if you wanted to contract it, you could just fold it in half. And that's a good, that's a good reminder that you can't just like subtract a certain amount. You're gonna have to use like the fractional differences. And then the shearing is what, yeah, it doesn't work as well with this. Okay, so shearing, can you guys hold it up for me? I'm done. Okay, so shearing is where we keep two of the points in the same spot and you kind of put it off to an angle. It's still a parallelogram and it still covers the same amount of area, but it's just shifted, like angles wise. So then if we wanted to shift these 2 points can stay the, yeah.
We'd like Emily and Jacob to hold it right where they're at and keep it there. Don't move
Yes.
your hands. But we'd like the other two people at the top to just move a little bit to some direction. Let's say to your left.
Yes, there you go. All right, so remember with these is that the blanket doesn't exactly show it, but this would be completely straight. There would be no give in a shear, so the shape wouldn't be changed at all, but it's still a parallelogram in its way that it changes. Yeah, that's just what I wanted to show you guys with a visual example.
So I do have a slide of the major things of each of the chapters. Most of you that are here have a test from the past, if you wanted to see your past mistakes or the big things. My plan is the ideas of your previous tests are the test-worthy things for the final. I'm not looking to deviate from those basic ideas. I'm starting with the new things. And then we'll kind of work our way into the assignment and then go from there. Just so I don't forget, if you have the final project thing, whether it was an application or whatever, I'll take that. So, new concepts, at least new as in you haven't been tested on it yet. Matrices that cause linear transformations. So you had an assignment that didn't exactly match exactly what we did in class, but the important portion is, can you show me what is the matrix that did that vertical shear, or that horizontal shear, or that reflection over the x-axis or across the x-axis, whatever it's causing it. And I actually think, from doing the same assignment that you did, that the answers themselves aren't that tough. Like in some cases, like number 1, do you need the matrix to come up with all the answers? Once you know you're just changing the y's or you're just changing the x's to the opposite, it was fairly simple to be able to do. The rest of this we'll come back to later, but how to make your least square from that column of 1s, RREF and all of that, cross products, etc. Let's backtrack. So from the assignment that was previewed, the 6.5 question that you want to go through, things that you're not sure about, something that threw you off. Caddy? So 47 says you get to that matrix by using 2, 0, 0, 1 and 1, 0, 2, 1.
So the first one is just an expansion of x.
Okay, so let's just talk about both of these first, and then we'll put all the pieces together. This is what I would say is a test-worthy thing. So in the first matrix, what's that do? Sure. So horizontal stretch, horizontal expansion. It doesn't really matter what you use. I'm just going to use stretch, because I think that's the algebra words that are used a lot. Horizontal stretch by a factor of 2. Everything that's x is twice as big. 110 turns into 210. You get the idea. This we didn't talk about as much, but it's going to be some sort of a shear. The way that I look at it is the original values stay the same, but then something gets added to it. So in this case, it's a vertical shear or a horizontal shear, and how do you know? So you're saying it's a vertical, it's a Y shear. I actually want you to talk to each other for just a minute. You had some problems with this, problems and problems with problems. Matt kind of hinted at it. So talk about it. And you know that because of the column it's on. Okay, so I heard a lot of people say the same thing. Matt, back to what you said originally.
It's a vertical shear because we're adding a component of x to y.
Okay? Because it's literally, if this is what's affecting my y, I'm taking however much x I have and I'm adding that to it. Okay, so now here's the toughest question that I would say at best we did poorly on Wednesday. And by we, I'll just say I. Which happens first, and then which one happens if the question is saying you want to end up with 2, 0, 2, 1. And I'm going to talk about it linear algebraically, but then also just with if you do this first and then you do that next, what's going to happen? So what happens first, and then what happens next if you want to end up with a shear and the stretch? It has to be one thing first and then the other. Kira, whatever you say I'll work with, whether it's right or wrong.
Well, it's the vertical shear first.
Because
Well, if you're taking, obviously the algebra just works out.
if I'm gonna just take, so you're right, I have to vertically shear this first, then horizontally stretch. If I stretched first and then added that component in a vertical shear, I'm adding the stretched to what's already there. I'd have issues if I stretched it first and then sheared the stretch, if that makes sense. If I went this, then technically it's already stretched and I'd be adding double the stretched value to where it's at. It could also go back to when we did elementary row operations, which is a hint on something that you might need to review a little bit. The things like this matrix will flip the order of the rows or the columns or some of the ideas that are similar to this. You always worked from this was first and then this was next and then this was next. It was like E1, E2, E3, E4. So the same reasons apply, but now we have like physical movements that are showing you why it has to be this, then this, then this, then this. Shisun.
So we do want to add first and then split.
If your goal is to have a set amount of stretch that's given in one of the matrices, then yes. So technically you could say, I could switch this if I change this to a 1. Like stretch it twice as far and then move the twice as far over, and then you could still get the same answer. Like, do you understand what I'm saying? Yeah, you're just nodding. But. So yes, in general, yes. Stretch at the end. Yeah, there's some ifs to that, but that's okay. Right, dynamic versus static stretching.
That's how you can connect to your sport people.
Right, Matt is now connected. Okay.
No, I'm not connected.
Hello, Mrs. Tessmer, as you're watching this on YouTube later. Anywhere else 6.5 that caused major problems? I'm not planning on 59 or 57 being on your test. Even though it was explained well with why you're doing different pieces with it, what I'm saying is the drawing the way that it is. But so what I envision then that you need to be able to do, if I'm comparing what the book asks you to do to what I want you to do, is if I asked you a problem like number 11, they had some notation that isn't wrong, and if you looked at the Calc Chat version, they really didn't show you at all the matrix that got you there. They had some other notation. You should be able to look at this and say, okay, I'm doing a transformation to some points, call them x and y. and I want them to transform into something like this, then you should be able to understand what kind of a shear this is, and connect that to that. So I'll say it again a different way. When I look at this, it's not that complicated in my mind because I can make the connection between this, and we already talked about, oh, that's a horizontal shear. I'm adding 3 of the vertical to the horizontal, and it's being shifted horizontally. Good enough with it? Okay, so what we're going to do in basically 5 minutes each is most of you have your tests right in front of you. If you want them, have them. We're going to do about 5 minutes of each chapter. It's going to be about a minute and a half by yourself or with somebody that's nearby you. And then the rest will be what's the worst. So when I looked at chapter 1, you can see the biggest ideas up there. Solving a system of equations multiple ways. REF or RREF by hand. It could be called Gauss-Jordan elimination. And then fitting 3 points to a parabola. All of those are in your test. And all of this will be in a PDF if you want the document of this some other time. But I'll be quiet, either by yourself, the review in your book, your test, wherever, but familiarize yourself.
This one I switched around number 11. Switched around that because they're high.
Oh.
How contested are so easy, seems so tough.
I don't fall apart at the school stuff. Not just in this class,
It's
like
kind of cool to
other
watch
classes.
here because everything is backwards.
Mm-hmm.
So you're writing that matrix, you're writing like your 3's backwards and stuff like that. It's kind of cool.
So you have about 40 seconds. Big picture things. You're looking at what causes you the most concern. This is also saying everything else is not fair game. So I'm not going to find something obscure from 1.2 that was in an extension problem that we haven't talked about. To me, these are big takeaways that in most of your cases you should have to explain or use as a high school teacher. Okay, so open up to something that you definitely want to review with the 3 minutes for this chapter. Is that a hand caddy or nah? So I'm not planning, if you can't see what Lizzie put there, I'm not planning on an application problem with motion paths or irrigation wells or whatever was there. But you definitely will have to take something of a 3x4-ish size that I know works out moderately clean. And you should know how to take this to where it needs to go. So I don't really care, if your first step is I want to multiply everything in the first row by a half. I don't really care if you use this kind of a notation like row 1 becomes a new row 1 like this, or if you want to go a little bit farther and say the matrix that got me there was like this. Whatever way makes it easier for you to understand. Both notations are fine. If the problem asks you what was the elementary matrix that took you from this to this, then obviously you need to know the matrix. Good.
I was looking ahead, always.
Okay. Fitting 3 points to a parabola. to me, the big idea is if you know the standard form of a parabola, then you should be in really good shape with just take your points, plug in your x and your y, and I should actually go like this. Plug in your x and your y, solve it for what's left. You can use multiple methods. My plan is not to give you 100 points, though, on basic substitution, elimination, and graphing where they intersect. Most of you are saying, move on, I should have got a perfect score on the first test. Okay, chapter 2, big picture ideas. You need to know how to do the basic matrix operations, the toughest of which is explain to me a little bit how a matrix multiplication works. There's a couple ways to do an inverse matrix. So one of which is using 1 over the determinant. There's another way to get an inverse by using adjoint matrix, or calculator not being one of them, or taking it and lumping an identity matrix on the end and solving it if that doesn't make sense. I'll show you if you need to. Elementary row operations, we just hinted at that. And I don't have the final test completely done because I want to see what it looks like in my head as far as time goes. But right now, I would say a big thing for Chapter 2 for points was build an LU factorization from a matrix. So I'll be quiet, page through, review. I would expect you will. I'm going to answer Lizzie's question kind of indirectly. So you do need, in the future, to know, okay, how to find a minor or cofactor from each of the values. Like, row 1, column 1 gives me this or that or the other, or the idea of an adjoint matrix. So your question was, are we going to have to do a 3 by 3? My plan is yes, but probably you should use a method that was faster than what you did in this test. You had to adjoin 1, 0, 0, 0, 1, 0, 0, 0, 1 onto it and take it through all the steps by hand. There's more efficient ways to get there. And most of you give me the look like, I think Chapter 2 doesn't scare me, or... Sure, so if I had some sort of a matrix, just in general, I think it'd be good to just review, like, what do you build first? Do you build the L or do you build the U, and how does that work?
Whatever one is closer to being there.
Because the idea is when you build one, the operations, the inverse of those operations give you the other. So the way that we went to it was, like, first of all, build your upper. And the way that you built your upper matrix, if I had something like, I need to make it so that, once again, upper matrix has all the numbers on the top, so I need to get rid of this value here. Okay? The way that I do it with LU factorization is I can't just do like -4 of this plus 3 of this. I can only do one operation at a time. So I probably am doing something like, I'm going to take and everything in the first row is going to be 1/3 as big as what it was before. So the operation that got me there is this. Now let's kind of keep that in the back of my mind. The next thing that I want to do is I want to take -4 of this and add it to this. So I'll show the answer first. So -4 plus this is this. -4 of this plus this is 16/3. Everything else stays the same. So what I did in an elementary, so like this is elementary matrix number 1. I'm going to ask you. So if I wanted to do -4 of this plus 1 of this, and the answer is going to end up on the bottom, how do you do that? Like, what's the row? Like, it's just something like this. Like, I want -4 of this plus this. So those are the two operations that were needed to build this. So my upper matrix in this case is something like this. My lower matrix is based off of the inverse of the elementary matrices. So in this case, using +4 and the reciprocal of whatever it is that I was doing with the other part. And that's kind of how you build either reciprocal if you're using multiplicative or the opposite if you're adding. And then you have a lower and an upper multiply together. For some of you that are giving me the look like, that's probably worth look for a review problem at the end of chapter 2. Good.
Did we already talk about whether or not we're going to find inverses by adjoining stuff?
I'm leaning towards no for the sake of time.
Cool.
So to Lizzie's question, I think you can use that method, but it's not the fastest.
Okay.
So let's go slightly faster. Chapter 3, it's all about determinants. I do think that you need to think about a bunch of things with determinants, like, do you remember what happens if you switch rows, and can you multiply by a number, and how does that affect the determinant, and what did making zeros do, or making a column of zeros, or a row of zeros, or all these determinant things. I'll be quiet, but I do think you should look through some of your work for chapter 3. And a lot of it has to do with what's allowable as you find determinants. And then indirectly, I'm going to answer Matt's question in about a minute and a half. That was, what's the other way to find the inverse that's not a calculator then? So we'll get there in a sec. So give me a connection. So cofactors to, or minors, like what's the basic idea, Jacob? What do you remember? What comes to your mind?
Cofactor is the determinant of each smaller person.
Sure, so it's just like what he was showing you here. So the minor is finding this determinant, cofactors when you double check and make sure, do I switch it to the opposite based off of row 1, column 1, row 1, column 2, row 3, column, you get the idea. Okay. Determinant multiple ways means you should know that some operations will get you there faster. Like I can switch rows and columns all I want. And if I make zeros, I can play the determinant game a little bit faster. Like for example, if I said find the determinant of and I said show your work for how to get there, I would hope that most of you focus on I can use this row to find the determinant, and I really only need -1 because it's in row 1, column 2, times the determinant of the pieces that are left. If I'm speaking gibberish here, then you probably should review a little bit. Maybe there's another operation that you have to do to get there, but just remember, like if I needed to multiply this column by 2, that just means the determinant is twice as big or something else like that. Page 129 has what I would call the money formula, and that's this. To answer Matt's question, if I wanted to find an inverse matrix that's bigger, like a 3 by 3, I would say the faster way is probably find the determinant and then find the adjoint. Adjoint is you need all of the cofactors, you transpose it, and then you multiply. Now, it really depends on how tough or how big are the numbers and all that kind of stuff. You will have the ability to use your calculator, but there will be problems where I want to see how you got it. So if I'm expecting the worst in a couple of you, you'll know you're right or you'll know you're wrong. You know what I'm saying? Like, I know what the answer is supposed to be and I can't get this to work. But Chapter 4. This is just the 3 or 4 minute overview. Really had to do with vector spaces and what did they span or had for subspaces. So vector spaces at the top here are the rest of the big words. Like how did you know it spanned everything? How do you know that they're linearly dependent or independent? What does that mean? How do you take and find the RREF and figure out this is the dimension or this is the rank? I'm just touching big picture things. I'll be quiet for a minute or so. Page through, take a look. All of these, you could find decent review problems at the end of the chapter too. Go ahead, Matt.
Are we going to do anything with conics?
So give me every last thing on the sentence. My plan is not that we have to review conic stuff.
Okay.
I actually don't think that's the toughest thing for many of you, but you don't need to review the discriminants to identify the shape and that kind of stuff. Because otherwise Lizzie wouldn't be prophetic that this class is really just matrix algebra.
It is.
I know. 80%, 80 and 90%.
Everything I think we do has an impact, or could be.
That's what Keanu Reeves told you is true too. So. Nothing, bad joke. What? The Matrix. Numbers falling from the sky.
I couldn't trust the
See the
Matrix
code.
on it, it was disturbing.
So anything from your test questions that you're not sure about, things that you want to look at? I know I got this right, but I have no idea how I got it. Go ahead, Jacob.
Something with dimension.
Okay, do you have a question that had it?
Number 13, 14, test. I don't know how to do this, so I use my skips.
Oh,
So, somebody else want to explain basically what dimension means?
that's like the number of vectors you need to form a basis.
Okay, do you want to go farther, Emily? Or is that what you're going to say?
That's fine.
Or to span it, right? Span or form a basis.
So I would say number of vectors needed to span the entire whatever,
Subspace.
right?
Vector space.
Right? So it could be like, if we're talking about spanning all of R3, you need 3 vectors. If you're talking about I want to span all of 2 by 3 matrices, I need 6.
You want to span
A polynomial.
polynomial that's 1 higher.
Right.
So P4, you need 5.
And
those were the 3 big ones that we talked
Right.
about.
I won't go outside of that. So it's basically saying, like, how many terms do you know you need to for sure span all of it?
To not be underdetermined.
Correct.
So on the test, the answers were 6 and 6.
They were. But if you didn't know what you're doing, then you could have guessed random numbers and been... The idea of rank is just basically in RREF form, or just looking at it like how many leading ones do I know I have, and kind of build stuff off of that. That's a really, really shortcut version of whatever it might be. Okay. And then your last one had to do with, so now take vectors and find their magnitudes, find their angle between the vectors, dot products, orthogonal, orthonormal. Those are big picture things. My plan is not to put a bunch of formulas on the test. So I don't know if something like angle between the vectors scares you, that you need to memorize something or not. So for some people, I think you might need to review. I have 3 vectors. I want to orthonormalize them to each other. How is it that I first of all make them orthogonal, the whole subtract and dot product go backwards? I'm not going to go beyond 3 vectors of 3 dimensions like what you had on the test. I'm not looking at a 6-dimension 25-minute problem just because we can. And then the new things that you don't have a test on are, do you remember how to do things like U cross V with IJK, all that kind of stuff, and what that's telling you? Some basic areas. We did area triangle, area parallelogram. They're basically related to each other. Just find the magnitude of that cross vector. Some basic transformations. By that I'm saying, like, I might give you stuff that has nothing to do necessarily directly to what Matt was talking about, but just, hey, this rule says apply this transformation, so apply it. What's the pre-image and what's the image kind of stuff? Go ahead, Emily.
I was just going to ask if we're going to have to prove like the inner product thing before
I'm not planning on a deep knowledge that you have to pull out 4 axioms or 5. Like, there's another problem and want to test it, like, what were the 10 ways that prove this or that you won't. The last thing that may be on the test is some sort of an application thing where you're going to have to take a concept and I'd like you to apply, like, so give me something that you learned from this class and how it's going to apply to how you want to teach it as you teach Algebra 2 or Algebra 1 or something like that someday. Usually that's not a very difficult problem to earn the full points on, but just so that you're not surprised. It'll either be that, or when I'm going through the practice, or going through tests, there'll just be too much time and we won't be able to do it. But be prepared that I want to see or hear what you think you need to take away with this towards the future. Go ahead.
We're not doing anything with mathematicians.
There is not a mathematician review piece on there. And the reason for that is just from my experiences, you'll spend 80% of your time on something that's worth probably 15% of the points. I don't think that is a bad experience. It doesn't say that you wasted your time with it, but I don't need you to go through all their presentations to remember who was German and who was French.
Cauchy was French.
Okay.
That's all you need to remember. The rest of them were German, probably.
Most likely.
Sad part is everybody could tell you that Cauchy was the presentation you gave, but nothing else.
Yeah, she's the one for the longest.
20 minutes of greatness.
20 minutes of a great mathematician.
That was when your blood sugar was... No.
Yeah, who knows what was going on then.
Okay. I would love the tests back in a stack that it came from. If you gave me the project stuff, that's fine. If you need to give me something sooner is better than later, but you'll be fine as long as it's before the test. Monday at 10? 12:30? Monday at 12:30? Feel free to shoot me emails if something major comes up before then. Otherwise, I think you're in pretty good shape. We'll see you then.
My last math class at overseas.
Really?
Last content class.